Hello, Bio30. Welcome to Probability. We are going to be learning about how the chances of certain things occurring can be figured out through probability. You've actually already been doing this by figuring out genotypic and phenotypic ratios. So let's get started. When calculating probability in genetics, it's very useful to determine the probability of a chance event occurring. So what are the chances that certain events are occurring? I need you to remember, and this is something you've probably heard in probability before, that events that have happened prior to the event you are looking at have no effect on it. So, for example, if I had a coin and I was flipping a coin, every time I flip that coin, I have a 50-50 chance, 50% chance of getting heads or 50% chance of getting tails. If I flip the coin and I get heads the first time, and I'm going to flip the coin a second time, getting heads the first time has no effect on how I flip this coin the second time. That's also now applying it to genetics. So just because you have 3 daughters does not mean that you will have a 100% chance of having a 4th daughter. Instead, you would have 1/2, because 50%, 1/2, you'd have 1/2 times 1/2 times 1/2 times 1/2. Every event is its own event. So you would have 50% chance each time, multiplying them together to give you the overall probability. We talk about probability in the form of this equation. Probability is the number of chances of an event divided by the number of possible outcomes or combinations. Like I said, you've already kind of been doing probability as you've been doing your genotypic and phenotypic ratios. If I asked you what is the phenotypic ratio of the cross and you say 3-to-1, well, you're telling me 3 out of 4 of the things are one thing and 1 out of the 4 is the other. So you're already doing probability, just in the sense of doing them in ratios to show them in a comparison. What we're going to build on is, you kind of already understand probability, I hope. We're going to add this idea of the product rule, which is using to calculate probability of 2 different events occurring at the same time. So here is the product rule. It's the probability of event 1 multiplied by the probability of event 2. What that means, ladies and gentlemen, is let's pretend you know someone who's going to have a baby, and they don't know what the sex of the baby is, boy or girl. Let's say they also have a really rare genetic condition in which they have all their toenails are ingrown toenails. You, as a geneticist or someone who's taken a beautiful class called Bio30, you could figure out the probability of this happening to the child if you knew how the genetic disease was passed. So, for example, you would say, okay, the probability of them having a son, for example, would be 1 out of 2. That's the first event. They don't know the sex of the baby. So what is the possibility they'll have a son? It's 1 out of 2. Now let's pretend that the linkage of the trait of ingrown toenails is recessive. So in order to get it, you have to have both recessive genes. You're going to say it is a 25% chance, so 1 out of 4. So you would take 1/2 times 1/4, and that would be the overall probability of them being a boy born with ingrown toenails. So that's kind of the idea here. So let's start with an example. You have this example in your notes, so just follow along and fill it out as we go. To calculate the probability of producing a son who is bractylactic from the following cross: bractylactic mother, whose mother had normal finger length, and a normal finger father. Short fingers are dominant to normal length fingers. Okay, so let's look at how we're going to set this up. First, we're going to come up with a legend. Here is my legend. Being brachdactyly is a big B, and normal length fingers is a little b. I'm going to figure out the chances overall of someone being brachdactyly or having normal fingers. So I'm going to cross my parents. So in here it says a mother who is brachdactylic, but whose mother had normal finger lengths. So we know she is heterozygous. That is who this big B, little b individual is the mother. And we have a normal length finger father, which means he has to have both recessive genes. So we are going to cross them, fill out their gametes, and put their gametes into our Punnett square. We're now going to do our cross. We have the following. There we go. So if I look at this overall, I can see 2 out of the 4 are brachdactyly, and 2 out of the 4 are normal finger. But this says calculate the probability of producing a son. They don't know what they're having. So again, it's a 50% chance. We now look at the Punnett square and we say, oh, it's also a 50% chance that this person is born with brachdactyly. So what we do is we figure out the two probabilities. 0.5 for the brachdactyly, 0.5 for having a boy, because remember, girl or boy, and you're going to multiply them together in the product rule to give you 0.25 or 25%. You can do this in fraction form. You could have gone 1 over 2 times 1 over 2 to give you 1 over 4, which also gives you 25%. Again, the key part here, guys, is that they did not know they were producing a son. It says calculate the probability of producing a son. There are going to be questions that you come across that'll say, calculate the probability of their son. So they already know they have a son, or their daughter. They already know they have a daughter. So in that case, you wouldn't have to do the product rule because you already know what the sex of the child is. Another example is a hemophilia or X-linked recessive trait. So we have a cross between a mother who carries the trait and a father who has hemophilia. From earlier video today, we know that X-linked needs to have an X attached to the allele. So this is normal, and this is hemophilia. It is a recessive disease. So X big H is for normal, X little h is for hemophilia. The mother, okay, is a carrier. It says a cross between a mother who's a carrier. Carriers are heterozygous individuals. So she is X big H, X little h, remembering the X because this is X-linked. And then the father has hemophilia. Now, because this is on the sex chromosomes, dad has only one X, so he is X little h, and then he has a Y. We are going to separate them out into gametes and put them into our Punnett square. When I do my cross, I can see what the daughters and the sons all have when I look at the Punnett square. There's my Punnett square. Now, here's where it gets a little bit tricky. I'm showing you this example because students all the time want to use X-linked traits with the product rule. Don't do it. It doesn't work out every single time, okay? X-linked traits are unique in the sense that some of the time it works out with the product rule, the other time it doesn't. Instead, just look at the entire Punnett square. And look at the Punnett square even if you're unsure of the baby's sex, okay? But this one says, what is the chances of them producing a daughter that has hemophilia? Well, I can look at my Punnett square and I can see here's the daughters and here's my chance of producing hemophilia. So in that case, it's 1 out of 4. So one daughter who has hemophilia, which is 25%. In this case, the product rule would work. This is one of those cases where it would work, where I would say, okay, what is my chances of having a daughter? 50%. And then out of the daughters, what is the chance of having hemophilia? It's 50% because there's only 2 options. So you would end up with 25% in the end. But it does not work every time. So please, please, please remember, when doing X-linked questions, do not worry about the product rule. Just find the normal probability. So those are the 2 examples I wanted to run through. During your practice questions on sex linkage, you will run into product rules and probability. If you have any questions, please let me know.